Hello everybody, my name is Jason Gregerson. This video is going to be on numerical methods for integration. We're going to talk about three main points in this video. The first is going to be why. Why are we going to use a numerical method versus an analytical method to do an integral? Two is how are we actually going to perform a numerical method. And we're going to talk about four main approaches: the left and right hand sums, midpoint rule, trap rule, and Simpson's rule. And lastly, some results about our approximations. So those are going to be our three main talking points. So first of all, why? Why are we using numerical methods versus analytical methods? And so there's three main reasons. The first one says because we can't find an antiderivative for some integrals. So we'd like to be able to use analytical methods, but for instance, this integral of sine x over x, we can't find a nice simple antiderivative that would allow us to complete this integration. So we can't use by parts or substitution or anything, in fact, to find an antiderivative. So we just can't use an analytical method. Number two says in real life our information is often data, not a function. So for instance, if we're given some data points and trying to integrate using these points, we don't have a function to find an antiderivative. So an example of that could be something like this. I have a tree. I want to find the volume of this tree. Well, I'm able to calculate the volume using an integral. And so we'll learn more about that in the next chapter, but there is a way I can use an integral to find out that volume element. But I don't have a function that represents maybe the radius of this tree. Instead, I have its radius value at different intervals. So here I'm not going to be able to find my solution by integrating a function, but I can use numerical methods on the data points that I'm given. The third reason is that it can be quicker or more efficient to find an approximate value to the integral than it can to find analytical solutions. So for instance, if we're using integration to maybe find an approximate solution to a differential equation or something in a larger problem, we may have to do 10,000 integrals in that process. And if in Mathematica or some other program, it takes a lot longer to find an analytic solution, it might be faster for us to use a numerical technique to find an approximate solution, since we're looking for an approximate solution to some other problem anyway. So those are the three main reasons why we might use a numerical method as opposed to an analytic method. Next, we want to look at how. How are we going to use this numerical method? So we're going to start off by looking at the definition of the integral. And so we have it written here. It's the limit as delta x goes to 0 of the sum of the function f of x sub I and delta xi, where xi is some x value inside that interval. So what does this mean? We want to find the integral of this function from a to b. And so we're looking for the area underneath this curve. And so one thing we can do is break this down into a whole bunch of little intervals and look at some random interval in the middle and say we're going to treat this like it's a rectangle instead of a curve on top. And so if we can approximate the value of that rectangle, we can ballpark the area underneath the curve. And our definition here says that if we take the limit of this process as these intervals get very, very small, that will give us the exact value of the integral. And so we're going to change that to find our approximate value by just not taking the limit. Instead, we can dictate how big we want that interval to be, and then we'll be able to find out our approximate value. And so really, all we're doing is replacing this with just the sum instead of the limit. And so these are really the two components that we have to figure out. Now the delta x sub I is just the width of these intervals. And so the problems we're going to look at, we're going to use a standard width for all these intervals. And so we're going to be able to set this and change this depending on how accurate we want our guess to be. What's really going to vary from our different techniques is how we find this value, this f of xi. And so we're going to have four different methods to find what we're going to approximate as the height of this rectangle. So now we'll look at the four main techniques for finding that height value for the rectangles. Now I say four, but I have five listed here, and that's because the right hand and left hand are basically the same kind of technique. So how are we going to use these different techniques? So I have my function drawn here, and I've divided the interval into subintervals. And I'm going to label the points at each side of those with an x value. So that's x sub 0, x sub 1, x sub 2, x sub 3, 4, and 5. Now we're going to look at the first rectangle that we're going to draw. And the right-hand technique says that out of that box, so here's the base of our box, delta x. Now to approximate the height, we're going to use the function evaluated at the right-hand side of that box. So the x sub 0 is the left side, the x sub 1 is the right side. So I'm going to take the function value, the height, at that point, and I'm going to use that as my approximate height for that rectangle. So for the next interval, I'll use the right-hand side of that interval. So x sub 1 is on the left, x sub 2 is on the right. This would be that approximate height for that rectangle, and so on and so forth. And so what this would look like would be the function evaluated x sub 1 times the base. That'd be the first box. The second box would be the function evaluated at x2 times the base. The third would be the function evaluated at x sub 3 times the base. Then evaluated x sub 4 times the base. And then the function evaluated x sub 5 times the base. Now what we can do is rewrite this into summation notation, which says we're going to add up I starting at, since the first x sub value we used was 1, we'll start at 1, f of x sub I delta x, and we'll go from 1 up to 5 in this case. And notice also that we have 5 different subintervals. So we're going from I equals 1 up to n, where n is the number of intervals. And so that would be how we can find a right-hand approximation. Now the left is going to be very similar, except instead of using the right side of the box, we're going to use the left side of the box. All right, so that's going to look a little bit different. I'm going to draw that one in red. It says for the first one, x sub 0 is how we're going to approximate that height. And so if I shade that in, that would be the first box using the left-hand rule. The second box would go up here to x sub 1 and go over like this. And so the formula is going to look very much the same, except where a little different is at the very last box, I'm approximating it here. So that would be the left-hand value, and that would be the last rectangle. And I'm not going to use f of x5 in this case. So for the first case, I didn't use f of x0, and for the left-hand case, I'm not going to use f of x5. And if I wrote this left-hand rule in summation notation, it would look like the sum from I equals 0. And here I'm going to go up to f of x4. But a way to generalize that, if I don't know how many intervals there are, if there are a lot of them, I would say n minus 1. So in this case, we have 5 different intervals, so that would be 5 minus 1, which would be 4, of f of xi delta x. So I'd be able to evaluate the function of those points. I'd have some known value for delta x, and I could actually add these things up. So really, if we look at the general format here, f of xi delta x, we're leaving delta x, and we're just using different ways to find this height value. The right-hand method says use the right-hand side of the box. The left-hand uses the left-hand side of the box, and the midpoint is going to use the middle value. All right. So how do I find that middle value? I'll draw it right in here for the first box. Well, it's just the average of the left-hand and right-hand x values. So that means it's going to be x sub 0 plus x sub 1 divided by 2. And that's where I'm evaluating the function. So it's f of that point times the interval. And I'll do that for each one of the subintervals. And that's how I do the midpoint. Now the trapezoid is a little bit different. The trapezoid is also going to work on the idea of an average, but instead of averaging the x values, it's going to average the function values. And so that's going to look like the function evaluated at the first endpoint plus the function evaluated at the other side of the box, divide that by 2, and that times delta x. Now we want to see what that actually looks like. So if I erase what I have here, and I'm going to just do this for the last box, what the midpoint rule says is that I'm going to use the midpoint value between x4 and x5 and evaluate the function there. That would be this value. And that's what I'm going to use to approximate the height of that box. And so that would be the value I use for the area here. Now what the trapezoid does is it takes the average of the function values. So what that's going to look like is if I plotted that f of x4 value and that f of x5 value, that average value is going to give me a line that connects those 2 points. right? So I'm actually going to form, instead of a rectangle, I'm going to form a trapezoid. With that as a rectangle and then the trapezoid kind of top to it. All right, so that's going to be a good approximation to that curve as we've drawn it here. And what we can see is that I'm approximating that part of the curve. Instead of using a constant value as I did before, the left-hand value says use this constant value, the right hand says use this constant value, and the midpoint says use this as my constant value for the height. But the trapezoid is fundamentally different because it approximates that function with a line instead of a curve. Instead of a constant. So now I have a linear approximation instead of just a constant. So it looks like that. And lastly, we have Simpson's rule. So the trapezoid kind of gave us an average of the function values, and Simpson's rule is going to give us a weighted average that we're going to use here. So what we're going to do here is we're going to take 2 times the midpoint value plus the trapezoid value. And since this is a weighted average, saying midpoint plus trap, and we're going to divide that by 3. And so this is going to be a weighted average of those values. So when we think about doing this, it's the exact midpoint value we use. So it's this value for the height. Take 2 of those, plus this value for the trapezoid. And we're going to add those 3 components together, divide that by 3, and that's going to represent the height that we're going to use inside a particular rectangle. Now we can use that to actually go piece by piece on the way through, or we can actually use the results of the midpoint and the results of the trapezoid rules and just take 2 times the result of the midpoint plus the trapezoid and divide by 3. And we're going to go through the calculations for these with some examples. But those are the basic definitions of how we use these techniques. Now let's go through some examples. So I have a specific function here. Here is my integral from 0 to 4 of x squared dx. And what we're going to do is divide this into 2 different intervals. So this will be our first interval, and this will be our second interval. And we're going to use these different approximating techniques to approximate this integral value. So the right-hand sum says we're going to use the right-hand value. So if my first point is 0 and the right-hand side of my box is at 2, I'm going to take the right-hand height, and this will look like what my rectangle looks like. And the next box will look like this. So in this case, my delta x, the width of my box, is going to be 2. I just got that from taking the total interval, the width of 4 from 0 to 4, and dividing it by how many boxes I wanted, dividing it by 2. So it's going to look like f of x1 delta x plus f of x2 delta x. In this case, f of x1 is going to be 2, so this is f of 2, and the width is going to be 2. And f of x2, so let me label those x sub 0, x sub 1, x sub 2. F of x2 is just f of 4, and once again that width is 2. Now what do I mean by f of 2? Well, that function is x squared. So x squared is my function, so f of 2 would be 2 squared. So there I have 4, and 4 squared is 16. And so 4 times 2 is 8. 16 times 2 is 32. My result is 40. This is my approximate value. The left-hand sum is going to be very similar. So one way I approximate a 40, left-hand sum gives me an approximate value of 8. Let's see what the midpoint gives me. So if I use my equation here, I'm taking the average of x sub 0 and x sub 1. So it would look like my first box would look like, and my second one would look like, well, x sub 0 is 0, x sub 1 is 2. When I average those values, I get 1. And I can see that 1 is the value that's in between 0 and 2. So really I'm using, this would be my first rectangle value. So f of 1 is 1, so I have 1 times delta x, which again is 2. And now just by looking at my picture, I can see that the average between 2 and 4 here, that point in the middle is 3. So the function evaluated at 3 would be 3 squared. So I have 9, once again, times delta x, which is 2. I'm going to have 2 plus 18, a value of 20. And now I'm going to look at my trapezoid values here. So the trapezoid value says instead of averaging the x values, average the function values. So it would be the function evaluated x sub 0 plus the function evaluated x sub 1 divided by 2 times delta x plus the function evaluated at the first point, the first side of the box, plus the function evaluated x2 divided by 2 delta x. So here I can just put in those values once again. F of x0 is 0 plus f of x1, so f of 2, which is 4, divided by 2. Once again, my width is 2. F of x1, remember x1 is the value of 2, so 2 squared is 4, plus 4 squared, which is 16, divided by 2, times delta x. And this looks like it's going to be 4 divided by 2, which is 2, times 2 is 4, plus 4 plus 16 is 20, divided by 2 is 10, times 2 is 20. So I get a value of 24. And lastly, I have Simpson's rule. And once again, I can go through this and do it per rectangle, but I don't have to at this point because I've already calculated the midpoint values and I've calculated the trapezoid values. So I can simplify my calculation for the Simpson's rule by saying that this is 2 times my midpoint approximation plus my trapezoid approximation and divide that by 3. So 2 times 20 is 40, plus 24 is 64 divided by 3, which will give me a value of 21 1/3. So I have all these different approximations to this integral. But the nice thing about this integral is I actually know what the value is. If I integrate x squared from 0 to 4, I'll get x cubed over 3 evaluated from 0 to 4. Now 4 cubed is 64, so I will get 64 thirds minus 0 cubed, which is 0. So this would be the exact value. So what we can see here is that the Simpson's rule actually gave me an exact value for this. And that's basically because I have a second order function here, and so this will approximate that. That is not always the case though, so where Simpson's will give me exact values. Very rarely the case, in fact. So that just worked out in this case. But it should be the better approximation. Other things we can note from here is that we can see that the right-hand sum gave me a much larger value, whereas the left-hand sum gave me a much smaller value. And we can actually justify that because in this special case of a function who's increasing all the way throughout, I can see that if I draw the boxes for my right-hand sum, that all those rectangles are going to be higher. And now I'm using 4 intervals for some reason, but we can see that all those boxes are overestimating the actual function value. And similarly, if I draw the left-hand sum, they will all be underneath it. So in the case where the function is strictly increasing, it's not going up or down, I can make that claim that the right-hand sum will always overestimate and the left-hand sum will always underestimate. So I can say that for sure. Now, if the function doesn't look like that, I'll draw a different function in here. If I have some other function like this where it's not strictly increasing or decreasing, I can't really make any strong claim about that. I could divide that function up into certain intervals and say, now in that area where it's just increasing, then I can say for sure whether something is an overestimate or underestimate. But in general, for the function over the whole region, I cannot say that. Also, the special thing about x squared is I can actually guarantee that the trapezoid value will also be an overestimate for this. And so if I use just one interval, or maybe 2 intervals to show this, I'll say that these will be my function values at the intervals. And what I explained earlier was the trapezoid is basically connecting those values with a line. And so that's one line, and this is the other line. And so as long as that function is concave up throughout that whole region, I can see that those trapezoid values will give me an overestimate. Now if it was concave down throughout the whole region, then I'd be able to say the trapezoid would be an underestimate. And so those are some observations we make about these approximations. So I'll summarize those points quickly here. So for increasing functions, the left-hand sum will be an underestimate, the right-hand sum will be an overestimate, and it has to be an increasing function. Decreasing will be the opposite, and one that's increasing and decreasing, I can't make any general statement, but rather I can break it down into subintervals and say it's an over or underestimate in those areas. And in fact, I can choose to use left-hand sums in one area, right-hand sums in the other, if I want to make some sort of more definite bound. For concave up functions, the trapezoid will yield an overestimate. For concave down, it will yield an underestimate. As we end this video, I want to ask 3 questions that you can explore as you leave. The first one says, how could we do this on a calculator or with Mathematica? Obviously, we want to use more intervals because we'll see that will give us a better approximation. But if I want to use n equals 100 or 1,000 or 10,000, that's something I obviously don't want to calculate by hand. So what would I have to do to write a program that will calculate this for me in Mathematica or on a TI calculator? The second question is, how do we know if our approximation is good? How do we decide whether your approximation is good and find out how good we need to make it or how many intervals we need to use to make it good? And also, what features about the function will also affect how good that approximation is? So those are 3 questions that we'll leave you with, and that will conclude this video.